can turn it on, that would be awesome. And so now that we're recording, does anyone have any questions about vectors? Anything you know, that you realized when you were doing homework wasn't clear yet? Okay, well, you know, Christian.
So once we know the components of the resultant, how do we find the angle?
So you'll find the angle using the inverse tangent. Let me put up the whiteboard and just show you an example. Okay, so oops. So suppose we, you know, add this vector and that vector, and we get a resultant vector. And the resultant vector, we can imagine it having, so this is r, maybe a minus, you know, 10 here and a 10 there. So that would come out to rx being minus 10 and ry being 10. So we always are going to find the angle by doing the inverse tangent of the y component over the x component. So in this case, this would be the inverse tangent of the y component is 10 and the x component is minus 10. So that's the inverse tangent of -1, which if you work that out on the calculator, you're going to get. And then you kind of check this and say, does that make sense? Well, -45 would be down here, but I know it should be up in the second quadrant. So, you know, so we're going to just add 180 to get 135. And that's how you're going to do it 100% of the time for an unknown angle of a vector. If you have its x and y components and you want to find the angle, you're going to do inverse tangent of its y component over its x component. And then at the end, you just check the angle to make sure it makes sense. And even if you don't have a picture, you can tell -45 doesn't make sense because the y component is positive. Okay, if the y component is positive, it means we're either in the first or second quadrant. And, you know, we got an angle that's in the fourth quadrant. So, but just by looking at the signs of these guys, we generally can tell if the angle we got makes sense or not. All right, so does that clarify it?
Yes, thank you.
Okay, no problem. All right, so today we're going to learn what we are going to do with the vectors. Now, you may still need more vector practice, and that is something that's dependent upon your personal sort of educational situation coming into here. If you haven't had math in a really long time, you may need extra practice even if you've seen this stuff. If you never saw it before, you know, additional practice can be beneficial. But as we take vectors back into the master equations of motion, we're going to continue to get reinforcement on how to find components and how to, you know, add components and how to find resultant vectors. All of those techniques that we learned in abstract last time. I mean, I should apologize for how boring it is to have a lecture on just vectors. It's not the most dynamic material, but we kind of learned about it in the abstract now, the math class version, and now today we're going to put it into context and see, you know, how we use it. So I'm going to go ahead and put up the simulation that you're going to be doing on your lab if you haven't done that yet, and just kind of show you a few details and use that to discuss you know, the next steps for us. So you're going to go to the link on the, you know, on the document, and you're going to see this thing, projectile motion. And you're going to pick the intro to begin with. And what we have here is a cannon, which if we press the fire cannon button, come on, cannon fire. There we go. We see a trajectory of the cannon. And we have tool, which is a tape measure. We can use that to measure distance. This says 20.91 meters. We can also put the target. The target sort of indicates 21.4 meters, and this is probably a little bit of just some of the, you can imagine the error associated with trying to visually line up this, this tape measurer. And we can also change the angle of the cannon, and if we do, we see a different trajectory. And we can even point it straight up if we want to. I wouldn't recommend doing this in practice, but if we point it straight up, then it simulates what we've been doing so far, projectile motion in one dimension. So far, when we've talked about acceleration due to gravity and free fall, we could only have something going straight up or, straight down. We can clear. Why did it do that? So we can, you can hit this eraser to clear things if it's, too crowded. So we can fire things straight down. Now, we are going to now learn, because of vectors, we're going to learn how to mathematically compute, for example, how this thing is in the air, how far it goes, how high it goes, all of the types of questions, how fast it's going when it hits the ground, all of the type of questions we could have answered for one-dimensional motion. And I'm just going to show you a few tools that we have here. By clear off everything, we can move our target. If you are, if you want, well, I guess you can't move that guy, but you can still, shoot him if you want to. I guess that's Michelangelo's David with shorts on. At any rate, we can also adjust the speed to try to hit the target. And it will generally display several trajectories that that sort of stay up, but they start to get a little fainter as we fire more and more projectiles. Eventually, the first ones will fade. So you can see that very first one that I did is eventually it disappears. Okay. Other tools here are, we can take this little device, and if we put the crosshairs at a certain point, one of these little dots, it will tell us the height, the range, which is basically delta y and delta x, and the time that this occurs. So you could use this to check your math on time of flight. You can even, when you're solving problems, you could open the simulation up, set up the same conditions, and check your math. So we can find out how long it takes for this particular one to hit the ground. It takes 2.24 seconds. So that's another useful tool. We can additionally show the acceleration vector. Okay, so there's my acceleration vector. As this thing goes, I can show the components of the acceleration vector. Well, this only has a y component, so that's not that interesting. But with the velocity vector, we can see the velocity sort of traveling along, always tangent to the path. And it gets kind of smaller and then bigger. And if it's going too fast for us, we can put the slow option. And then we can kind of watch it more carefully and see exactly what's happening. And I think the most interesting thing is looking at the components of the velocity vectors. So if we look at those components, what we see is the y component is always changing, but look what happens to the x component. I mean, it's from here to here. If I wanted to measure that, not that that measurement would have a great deal of meaning, because the units of that should be meters per second. But if I measure it at different times, it's always the same length. We can even step forward just one step at a time if we want to, and unfortunately we can't step backward. But so you're going to be using all of these tools on the lab. We can additionally add in air resistance. Okay, so if I add air resistance, let's make it normal. And that, with no air resistance, that same path would have looked like this. Okay, so those are some of the tools you're going to be working with, but I really wanted to use it just to point out a few things. First of all, the acceleration vector, if we fire, oh, you can fire two at once, I didn't realize that. But as we step along, you can see these acceleration vectors never change in size, and they're always vertical. Okay, they never have an x component. That means when we think of the acceleration as a vector, it itself has components. It has an x component and a y component, but its x component is always 0 because it never points to the right, it never points to the left, as long as there's no air resistance. Okay. The other thing important here is that the x component of the velocity never changes. Okay, so let's go back to the whiteboard. And does anyone have any questions about this this little simulation before I take it off? Okay. Okay, so let's look back at our master equations and try to see how vectors fit in. So our master equations, delta x equals v initial t plus 1/2 at squared. V final equals v initial plus at, and v final squared equals v initial squared plus 2a delta x. So those are our master kinematic equations. And 4 out of these 5 variables are actually vectors. So delta x is a vector, v initial is a vector, a is a vector, v final is a vector, but t is not a vector. Okay, so I'm just focusing on those 2 equations right now. For sort of technical reasons, these guys, when you square a vector, it's a little complicated. So let's not cloud the issue by thinking about what a squared vector is. But here, what we have is a vector being equal to another vector times a scalar. Keep in mind, again, time is a scalar because it wouldn't make sense to say north after the time duration. 3 seconds north doesn't make sense, but 3 meters per second north does make sense. Or 9.8 meters per second squared down makes sense. So when we have vectors and we add vectors, what we just learned yesterday is the only way to add vectors is to add up their components. So we have a delta x, and this looks a little funny, but in principle, we should imagine that there's an x component. Think of this like the r, the resultant x component. Okay, so we get the delta x by adding this vector and this vector. So delta x, x component should be v initial x component times time plus 1/2 a x component times time squared. And the y component of the displacement. Again, that looks funny because we have been a little sloppy using delta x for every direction. We used it for side to side when we were talking about a train or a girl on a bicycle, and we used it for up and down when we talked about dropping a coin out of a hot air balloon. And so that's kind of a generic displacement. And this would be the initial y component, t, plus 1/2 a y component, t squared, and so on. All of the equations work that way. We add up all of the x components of the things on the right to get the x component of the thing on the left. Add up the y components of the thing on the right to get the y component of the thing on the left. So we can just rename this because it's a little bit awkward. And what we're going to do is when we mean displacement in the x direction, we're just going to call this delta x. And when we mean displacement in the y direction, we're going to call that delta y. Okay? So our equations become, we have the x components over here and the y components over here. The x component equations are going to look like delta x equals v initial t plus 1/2 v initial x t plus 1/2 ax t squared. And on the right-hand side, we have delta y equals v initial y t plus 1/2 ay t squared. And if we take the second equation for v final, and we just look at x components, we get v final x component equals v initial x component plus a x component times t. And over here, v final y component equals v initial y component plus a y component t squared. Sorry, not t squared, just t. Now finally, this third equation. Remember, we got this third equation by combining these two and doing some algebra. Some of you did that for extra credit. So in the same way, we could combine these two to get a third master equation that looks like it's for x components. V final squared equals v final x squared equals v initial x squared plus 2ax delta x, and on the right-hand side, v final y squared equals v initial y squared plus 2ay delta y. Okay, so here are our master equations. Now we have 3 master equations for x components and 3 master equations for y components, and they're basically the same kind of thing. So it looks at first glance like it is exactly twice as hard to do 2-dimensional problems as it is to do 1-dimensional problems. But it's not quite correct. So first of all, how many variables did we have originally? Does anyone know how many variables we had in our original equations? Well, I mean, count them. Someone count the variables in the original equations before we wrote vectors on there, just the original equations. How many different variables are there?
Five.
You guys, what's that?
5.
5, exactly. So now that we've doubled our equations, how many variables do you think we have?
I think it's still 5, right?
Well, I mean, I'm thinking of VFX and VFY as 2 separate variables.
Oh.
So how many variables do we have now in our 6 master equations? Nobody wants to say 10, but some of you are thinking 10. It's not 10, it's 9. Okay, 9 variables. It's kind of a trick question, but nobody wanted to fall for it. That's okay, that's all right. So we have delta x and delta y. We have VIX and VIY. We have AX and AY. We have VFX and VFY. So all of our vector variables sort of double because we have x components and y components. but the time does not double. There's not a tx and a ty. So there's four pairs because of the vector components plus time. So there's 9 variables. Okay, so it's not quite twice as hard. It's almost twice as hard. There's twice as many equations. There's almost twice as many variables. But there's a further simplification that happens because what we saw with the acceleration vector. So just imagine we have a cliff and we kick a soccer ball off of the cliff with a certain initial velocity, and it travels along a parabolic path like what we saw in the simulation. And if we draw in the acceleration vector at different points, it just looks like this. Okay? It always looks the same. What we observed before and what I'm pointing out again is that this has no x components. It only has a y component. And so for every single problem that we do, we're going to have ax equals 0 and ay equals minus 9.8 meters per second squared. So that is, acceleration is a vector that points down. It points down because gravity points down. It doesn't matter if the thing's going up or on the way down. Gravity is always down, and so ay is always minus g. Okay? Now, because ax is 0, it allows me to do the following magic trick. So watch carefully. You have to pay very close attention to this magic trick and see if you can tell what I'm doing. You guys ready? Okay. Did you catch the trick? Let me show you again. I'll do it in slower motion. Okay, so here's the magic trick. I'm putting my eraser tool on, and anywhere I see an AX, I just erase the whole thing. Because if AX is 0, and I'm multiplying stuff by 0, that stuff is 0. Okay, it just kills it. So let's look at what happens to my x equations now that I did that magic trick. Let me pause and make sure there are no questions about that trick. Does everyone understand why? Raise your hand if you understand why I'm allowed to erase all that stuff. Okay, good. Now let's look at what remains. Equation number 2. V final x equals V initial x. So if I would draw in my velocity vectors over time, what we saw on that simulation is that, the size of the y component is always changing, but the size of the x component never changes. And that's all equation number 2 tells me. It says that the size of the x component never changes because there's no acceleration in the x direction. So if the initial velocity had maybe its magnitude was 10 meters per second, but the x component was 5 meters per second. So if we just did our trigonometry and found the length of this side based on the angle, it will stay 5 meters per second all the time, okay, the whole time. So equation number 2 is not actually an equation we really use for anything. It's just a reminder of a concept, that the x component of the velocity never changes. Now equation 3 is just equation 2 squared, so it doesn't tell us anything new. It says the exact same thing as equation 2, so why do we need it? We don't need it. So what really happens now, once we recognize that ax equals 0, and we're in 2 dimensions, is we really only have 4 equations that we will use. Okay, we will use these 4 equations. 3 of them are just exactly what we've been doing all along with hot air balloons and things. And the 4th one just tells us what's happening in the horizontal direction while all of this vertical motion is going on. So that 4th equation is also a very simple equation, because unlike equation number 1 in our old version, which was a quadratic equation, this is no longer quadratic because there's no 1/2 at squared term. So in practice, this becomes a very easy equation to solve. Okay? So to summarize, at first glance, it looks like going into 2-dimensional motion will be twice as hard as 1-dimensional motion. But really, instead of doubling the equations, we just get 1 extra equation. But we have the added benefit that we can draw a nice picture of the path of the trajectory, which actually makes it easier to interpret problems. So I would actually argue that once you get used to 2-dimensional projectile motion, it may even be easier than 1-dimensional motion, because it's very hard to draw a picture to visualize a girl like and her friend trying to catch her. But it's very easy to visualize someone kicking a soccer ball off of a cliff, because we can draw a picture and draw the path. So let's do that. Let's try to solve a problem using these new master equations. I'm going to just capture these equations and copy them to the next page. Oops. Let's put them up at the top. Come on. And I'm just going to get rid of what we don't need here. Okay, so those are our equations, just so we can see them as we work. Now, suppose we have, like I said, we've got a cliff, and maybe the height is 20 meters. And a soccer player, someone, name your favorite soccer player. Yeah.
Ronaldo?
Who's your favorite soccer player?
Ronaldo? I actually don't know much about soccer.
Ronaldo? Which Ronaldo? You have to be more specific. There's
Okay.
Brazilian Ronaldo, also known as Fat Ronaldo sometimes now, which is, I think, not kind, because, you know, he used to have to eat 8,000 calories a day, and now he's. But then there's Cristiano Ronaldo, the one who likes to sell underwear.
Yeah,
That guy?
Cristiano Ronaldo.
Okay, you fail. I'm sorry. No, I'm kidding. Okay, so suppose Cristiano Ronaldo kicks a soccer ball off of a 20-meter tall cliff. And the initial speed, he can kick a ball pretty fast. So suppose he kicks it at, let's say, 35 meters per second. And he does it, well, you know what? Let's make it a little simpler and let him kick it horizontally. We'll kind of ease into the work. So he kicks the ball horizontally at a speed of 35 meters per second, and we want to know how far it goes, okay, before it, you know, hits the ground. So we can draw a picture if we read that word problem. We see this nice parabolic path, and if we start to translate the problem, let me say it again. Cristiano Ronaldo kicks a soccer ball horizontally off of a 20-meter tall cliff with a speed of 35 meters per second. How far does it go? So if I wanted to translate that, I would say VI equals 35 meters per second. I would say that theta equals 0. So the angle that he kicks it is 0. Remember, all vectors kind of live on their own axes. So when we're measuring angles of vectors to find components, we have to imagine drawing axes at the tail of that vector. So the angle for that vector when we get around to finding components will be 0. And we can say ax equals 0 and ay equals negative g. We're being asked delta x equals question mark. And we're being told delta y. Now this is a little bit tricky because probably most students first time around would guess delta y equals 20 meters, but that's actually not correct. Anyone know what delta y would be in this case? Do we have a guess about that? Ziad?
Is it negative 20?
It is negative 20. So it's negative 20 because it's going downhill. Remember, delta y is sort of y final minus y initial, which would be 0 minus 20 meters. So we can say delta y equals negative 20 meters. This would be true even if this thing starts out going up. Its final height is 20 meters below its initial height. Okay, so here's my translation. We translated 1, 2, 3, 4 things. Now, these are translated things, but they do not appear in my master equations. So I'm not really done. Those two pieces of information are the polar form of the initial vector, velocity vector. But we don't want the polar form, we want the Cartesian form. So we have to find Vix and Viy from this information. Now, there's a couple ways we could proceed. The first way is if we've been working with vectors for a little while and if we're feeling comfortable with them, we can immediately say what Vix and Viy are without doing any work, okay, if we've built an intuition. But probably most of us are not at that point yet. So we would want to do work. We would use our formulas. Vix has to be Vi times the cosine of theta. Viy equals, oops, I already have Viy. Viy equals Vi times the sine of theta. So that's going to be 35 cosine of 0 meters per second and 35 sine of 0 meters per second. And if we plug that in the calculator, we get 35 meters per second and 0 meters per second. Again, we could intuitively know that this is the case because the V initial, it points strictly horizontally. So that entire 35 meters per second is all in the x direction. And there's nothing pointing up or down, nothing left to be in the y direction. But again, you may not have built that intuition yet, and that's totally fine. We will build that intuition as we go and see more examples and as you continue to practice. Okay, any questions about the components of VI? Okay, so now that we found Vix and Viy, we have information about 6 of the 9 variables. Okay, 6 of the 9 variables. Which variables do we not know anything about? Well, we haven't said anything about the time. and we haven't said anything about VFY, and we haven't said anything about VFX. But we know conceptually that VFX, that the X component never changes, so VFX is always 35. So there's really only two things that we haven't said anything about, and a third unknown, which is delta X. That's what we want to find. Now, let's try to solve for delta X. Look how easy this is going to be once we've translated. How many equations do we have that have delta X in them? One. This is a softball. It's an easy one. How many equations on the top of the page here have, yes, one equation only. So guess which equation we're going to use? That one. Okay, so here's my translation. I'm going to just block it off. And here's my solution. Delta X equals V initial X times time. Now, the V initial X, we know. So, but the time we do not know. So that tells us what to do next. We now need to solve for time. If I look over at my equations on the right, there's no more equations on the left that have time, so I have to come to the right. I see only two equations with time. The first equation has time as the only unknown, and the second equation has time and VFY as unknown. So I would like to pick the first equation. Delta Y equals VIY T plus 1/2 AY T squared. And we'll check what we know. We know delta Y, right? It's -20. We know VIY is 0, so I can cross out this whole thing. We know AY, and we know 1/2. So it's very easy for us to solve this for T squared, or for T. It's not even really necessary to use a quadratic formula because this piece canceled out. We just multiply both sides by 2 and divide both sides by AY. And this is T squared. So T would be the square root of 2. And I'm going to do a funny thing here. The delta Y, we could call this minus H. So I'm going to call it minus H in here. And AY, we can call that minus G. And when I do that, I can now see that those minus signs are just going to cancel out. And we have T equals the square root of 2H over G. Any questions so far? Remember, I'm going to keep insisting that we work with symbols as much as possible. This becomes more and more important as we go. So I'm going to copy this and put it on the next page so we can continue. And then we'll just try to solve for delta X, now that we know T. So delta X is equal to VIX, and remember, the VIX was the whole VI. The VI was 35, and VIX is the whole thing, so I'm just going to call that VI, which would be VI times the square root of 2H over G. Okay, so what I have now, it almost looks like a new master equation. It's a formula that will calculate the range of flight anytime we throw, kick, launch, toss, we eject something horizontally from a height h at a speed vi on a planet with a certain acceleration due to gravity. Now, in this particular case, it's Cristiano Ronaldo, and he's kicking at 35 meters per second from a 20-meter tall cliff on Earth, where g equals 9.8. But if we later put the actual best soccer player in the world, Lionel Messi, on top of the cliff, we can see how far he can kick the ball. So let's see what kind of number I get out of this. So that's going to be 70.7 meters. Now, I don't really write the units in all the way because I know as long as my g has meters per second squared and my h has meters, that the time has to wind up in seconds, and the v initials in meters per second. I know the units work out as long as I didn't make a mistake in my algebra. If all of my units are in the metric base units. Christian, question.
What number's in the parentheses in the square root?
On this line here, the
Yes.
actual numbers? Yeah, let me write that
Yes.
over a little bigger. So we have 35 times the square root of 2 times 20 over 9.8. Okay, now not only could we use this formula if we were going to do this kind of problem a lot to solve for the range, we could invert it. Suppose we know somebody kicked the ball 80 meters from the same cliff, kicking it horizontally, and we want to know how fast that person kicked it. Well, we know we would have delta x and h and g, and we could rearrange this for vi. So solving things symbolically is very beneficial because we can use those results, and it's sort of like we start building a catalog of new information. Now, having said that, I would strongly discourage you from trying to memorize this equation. What you really want is you want to use those four master equations to solve any problem there is. And if you instead start trying to memorize special equations for special situations to help you on tests, you wind up forgetting which equation works in which conditions, and it winds up being counterproductive. It's better to just work with the four master equations and learn a system so that you can solve any problem, anything that you come across. It's kind of like if you had one tool that would do any job. Why would you want a whole garage full of hundreds of tools just scattered all over that you have to search around and try to find this perfect tool that only does this one special thing? Maybe that goes for kitchen appliances too. If you have one super appliance that does everything, that might be preferable to having, just cabinets and drawers full of different, very, very specialized kitchen utensils. So we have these sort of super tools, and we want to just learn how to use them. And that is a much more efficient and faster process than developing hundreds and hundreds of special equations. All right, does anyone have any other questions about this problem? Let me just quickly summarize, because this is the first time we've done this. We got a problem in English. Somebody's kicking a ball horizontally off of a cliff with a certain height at a certain speed, and we want to know how far it goes. So what do? We translate first, just for. We know that ax equals 0 and ay equals minus g for basically every single problem in chapter 3. Additionally, we know we were given the V initial and the angle. The angle was given in English with the word horizontally. So that's a little bit more subtle than if it said at a 20-degree angle, for example. And we have to take this information and convert it into components. Additionally, we knew we were looking for delta x and we were given delta y. Here's another place we have to be careful, because just the fact that the height is 20 doesn't mean delta y is 20. We have to think about the direction, because delta y is a component of a vector. Just to show you where delta x and delta y, this thing here, this straight line, would be the displacement, and delta y is the sort of vertical direction, and delta x is the horizontal direction. So delta x and delta y are components of the displacement, which is defined as a straight line drawn between the starting point and the ending point. And then once we have done the translation, it's usually pretty easy, because there's not a lot of options which equation we can use. We picked the delta x equation. We saw that we would need time, and that required us to get the other side. And that is another feature that we will see time and time again. The time is the only variable that connects the left-hand side and the right-hand side. So we will always have to use the time as the bridge between the left-hand side, the x motion, and the right-hand side, the y motion. And once we did that, it was just a matter of some algebra to solve for t, plugging it back in. And we did it the hard way, getting an equation and then plugging in numbers. Again, I want to continue to encourage you to try to work that way. But if you're doing this in practice and you can't do it that way, go ahead and find a number for time, solve it. And once you've done it that way, go back and see if you can do it with symbols, so that you can make that connection in your mind, because that's a connection your math teachers and connection that you need. And once you have that connection, you're going to be so much stronger, like mentally, with your math skills. Okay, so let's try another problem. So normally, it's not a very horizontal line. Normally, soccer is played on a level field. So someone else name your favorite soccer player that's not Ronaldo. Okay, Robert Lewandowski, the striker at Bayern Munich. He's pretty awesome. I will agree. He's a heck of a striker. So let's say he is kicking a soccer ball on a level field, and he kicks it with an initial velocity of 40 meters per second, and maybe at a 20-degree angle. And we want to know, again, how far it goes. So draw a trajectory. Now notice this velocity vector, it is tangent to the path at the very first instant, but the path itself is always curving. Even if you are doing a problem with a cannonball or a bullet, something that should be going super fast, you should draw it very curvy so that you remember that this is not a straight line. Okay? That will help you avoid mistakes down the road. Now, if I want to translate this, I would probably just start with ax equals 0, ay equals minus g, because those are always the case. Vi equals 40 meters per second, and theta equals 20 degrees. We, again, are being asked the same kind of question, delta x equals question mark. So those are the easy ones, but we need more. So does anyone have an idea of what else we could add in the translation? And just whatever idea you have, it's almost better to have a wrong idea because you will learn that your idea is wrong than to have the right idea. So don't worry if you're right or wrong, but what do you think? What else can I say? Ziad?
So delta y would be 0 because we're at a level playing field.
Exactly. So delta y equals 0 because the initial height is 0 and the final height is 0. And so from start to end, it's sometimes good if you kind of label initial and final, because with this same picture, someone else might be asking how high does it go? And if they're asking how high it goes, then the final is at the top and we wouldn't have delta y equals 0. But this time our final is on the same level at the same height as the initial. Okay, so that should be enough for us to solve the problem. We want to find delta x, so we have delta x equals the initial x times, let's go ahead and, before I do that, let's find vix and viy. So vix is going to be vi cosine of theta, and viy is vi times the sine of theta. And I'm just going to leave them symbolic. We're not going to get even a number for vix or viy this time. We're just going to leave it symbolic, and we're going to solve the whole thing symbolically. And what we arrive at in the end is probably the one case where I would say this equation is useful enough that we're just going to add it to our equation sheet, because we will use this situation of something starting and stopping on the same level. Happens a lot, not just in soccer. So to solve for delta x, we use our master equation for delta x. Delta x equals vix times t, and this is going to be vi cosine of theta times time. And then we ask, do we know things? Do we know vi? Yes, we do. Do we know theta? Yes, we do. Do we know t? No, we don't. So we have to solve for t. Now, we're going to go back to our equations. On the y direction, we have two equations that have t. We're in the same boat that we don't know VFY, so we probably should pick equation 1. However, if we pick equation 2, we can still solve it, okay? So since we used equation 1 last time, I want to pick equation 2 just to show you what happens if you make the wrong choice, so that you can know there isn't really a wrong choice. There's really no way to fail as long as you keep working. So using the second equation, we would say VFY equals VIY plus AYT. And we check, do we know everything? Do we know VFY? No. Do we know VIY? Well, yes, we can consider we know it because we know VI and theta. So I'm just going to say we know it, because we could get it. Do we know AY? Yes. And we're trying to solve for T. So if we pick this equation, we cannot solve yet, but we find out that we just need to find VFY. So we go back to our equations. There's only one other equation with VFY. So there's absolutely no choice. We have to go to this third master equation. VFY squared equals VIY squared plus 2AY delta y. And then we, again, follow the same procedures. Check, do we know enough stuff? Do we know VIY? Yes, in principle. Do we know AY? Yes. Do we know 2? Yes. Do we know delta y? Yes, and it's 0, so it cancels out. And that means VFY is equal to plus or minus the square root of VIY squared. In other words, it's just plus or minus VIY. Okay? So why are we getting 2 answers? Because we're solving what's the velocity when delta y equals 0. Delta y is 0 at the beginning, and it's 0 again at the end. So one of these answers is what VFY is if no time passes at all. It just, we fire it and instantly measure. That would be the plus sign. On the other hand, our final velocity is over here. It should have a negative y component. So we can say that VFY equals negative VIY. So let's copy that, move it to the next page. And we can keep working. So this VFY equation, if we put in minus VIY equals VIY minus G times T, so I'm putting in that AY is minus G, we can now solve this for T. We're just going to subtract the VIY from both sides, so we wind up with a minus 2 VIY equals minus GT, and then T is minus 2 VIY over minus G. So those minus signs cancel out and leave us with 2. And instead of VIY, I'll put VI sine of theta over G. So we have an expression for the time, and we're finally able to substitute that in to our delta x equation. We have delta x equals VI cosine of theta times 2 VI sine of theta over G. Now, this is a done problem, or ready to plug numbers in. However, it's possible to simplify this expression and put it in a nicer looking form. Now, we've been at it for about an hour. I sense the energy is low, so we're going to pause for about 5 minutes and let you stretch, get a snack, whatever you need to do. And when we come back, we're going to simplify this. We'll do a little algebra to simplify it. And then we're going to get, like I said, a new sort of sub-master equation. It's not quite a master equation, but it's a new, very useful, very important equation that we can use on a lot of problems. All right, any questions before we take a break? Okay, Christian.
So when you're finding the components of the initial velocity, how do you decide when to use like cosine versus sine?
Basically, it's from our vector before, just in general, AX equals A cosine of theta, and AY equals A sine of theta. That's just generically true all the time. But the way I remember it is I think about a vector in the first quadrant. A. And then, you know, AX and AY would be here. And the AX is adjacent to the angle. And because it's adjacent, that's what reminds me that it's the cosine. And the AY is opposite, that's what reminds me it's the sine. So in practice, what I really do to remember it is I just think which one of these is opposite, and that one gets the sine. And the vertical one is the opposite one. Even in other quadrants, the picture's not so clear, but that I think in the first quadrant, which one is opposite, and that's how I remember it. All right, good. Other questions? Okay, let's take a fiver.